So we're going to tell you about two experiments that we're doing. One which is in a cylindrical system in the Couette flow geometry, and I'll tell you what that is. And another which is in the spherical geometry using the boundary condition I explained to you that we were going to use the boundary-driven flows. And so I'll show you how that works, okay? So plasmas, we talk about plasmas, we characterize plasmas in terms of their temperature. Plasmas are hot ionized gases. Liquid metals are different in some sense. The temperature plays an enormous role in determining the conductivity. The density plays a big role in determining the viscosity. We talk about the number of particles per cubic meter. This is very nearly a perfect vacuum. We introduce a few particles into the plasma. We ionize them. It can get very hot. 1 eV is 10,000 degrees C, or 10,000 degrees K. So a temperature of 10 eV or 20 eV corresponds to something like 200,000 degrees Celsius. Okay, so these are very hot gases. The electrons are stripped off of their ions. That's what makes a plasma. Okay? So this is a little bit of a punchline. I'll say it several times. Plasmas, we're now regularly making plasmas which have magnetic Reynolds numbers near 1,000. The Prandtl number, the ratio of these two things, is of order 1, and we can vary it. So plasma experiments offer several things that the liquid metal experiments can't do. One is we can go to much higher magnetic Reynolds number. And this means several things. One is we can go well above threshold. So instead of just finding the threshold, we can study how things behave as we go to higher magnetic Reynolds number.
In the left side you showed that's the RMC. Is it 16, what is 16, 20? Show the number 16. Earlier slide.
Yes?
Slide. 16. So that, achieved.
These are achieved, yes. And we're still learning. Yeah. So we can go well above the threshold for these dynamos to turn on. We can independently vary the viscosity and the conductivity, which means we can change RE and RM by adjusting the plasma parameters. In principle, this means we can go from laminar to turbulent flows. Plasmas have some compressibility effects. If we can optimize them, it might mean that we could do things like have stratification, which is important in some stellar models, for example. Buoyancy could be important. And then there are things that are beyond MHD in a plasma. So what's the role that neutrals play if they're present at the same time as plasma? Or what are the kinetic effects when the temperature can be different in different directions? When transport coefficients depend upon presence of magnetic field and so forth. And so we're in the process of now holding these plasmas, making them, confining them, stirring them, and doing this in such a way that most of the plasma we're looking at is unmagnetized. And I'll show you how we do that. So let me just tell you that the viscosity and the conductivity are functions of the plasma parameters. So I told you we know the density, we can measure it. We know what the ion temperature is, we can measure it. We know what the electron temperature is, we can measure it. Flow speeds are usually on the order of 10 kilometers per second. We can make plasmas flow very fast. And this makes it possible to get these big values, okay? The electron and ion temperature are often not the same. Usually the ions are much colder. The plasma is not in thermodynamic equilibrium in that sense. And so these are the sorts of numbers that we're talking about. So in order to make the plasma, the fluid Reynolds number big enough, I told you we needed the fluid Reynolds number to be big enough that I got lots of colloidal circulation, right? That means we need a minimum density, so it needs to be a dense plasma. We need to make it hot. It means we want the electron temperature to be as high as possible. This means we need lots of power. to make the heating as much as possible. And we need some confinement so it doesn't cool off. Okay. So I'm going to start out talking about accretion. And I know this is more astrophysical eye candy. This is a picture, a composite image in the radio and in the optical, and what you see are galaxies. And in the middle of this is a picture of a big galaxy. And in the center of this galaxy is a very active galactic nuclei, which is spitting out these magnetized jets of plasma. And this is, an AGN is a black hole that has matter rotating around it and is accreting the matter. This gives off X-rays. We can actually see that. And it has to be a dynamo, as it'll turn out. It's producing magnetic field that is observed in these jets that's spewing out in both directions. And a really interesting property of this system is that if you convert the amount of matter which is being accreted, the energy that's available and being liberated, something like 10% of the rest mass energy of the falling matter actually shows up as kinetic energy and magnetic field energy in these plasma plumes which show up. 10% of the rest mass energy is a factor of 10 more efficient than nuclear fusion as a nuclear power source, for example. It's an extremely efficient way, and it magnetizes the universe. So accretion is a big problem in astrophysics, and it's kind of a dynamo problem, as you'll see. So if you look at this central thing, what happens in an accretion disk is you have plasma that's rotating around some supermassive black hole. It forms a disk, it compresses, it has angular momentum. If the matter doesn't lose its angular momentum, it simply stays in a stable orbit around the central object and never falls in. In order for matter to fall in, it has to lose angular momentum to drop in and accrete. The observed accretion rates are too fast to be explained by normal viscous coupling of momentum. Something is needed. And one of the theories for how matter might accrete more efficiently is based upon a dynamo model ultimately and something called the magneto rotational instability. So in an accretion disk or near a star, the planets are going very fast, and farther away they rotate more slowly. Plasma around an accretion disk would do the same thing. So near the center, there's a lot of rotation. Near the outside, it's very slowly rotating, right? So now imagine that you take a magnetic field that seeds through this flow, and imagine two fluid elements which are connected by a field line, and perturb this field line so that this fluid element moves a little bit closer, and this fluid element moves a little bit further out, right? And then we'll use the frozen in flux idea to think about how those two field lines will be stretched apart. So what would happen is the central one is sitting here. It's rotating more quickly around than the outside. And what this leads to is it leads to stretching of the field line, which is increased magnetic tension. That causes this element here to slow down. As it slows down, it loses angular momentum and it falls closer to the center. The one on the outside is sped up. It moves to a bigger orbit, and this gives a runaway effect, which is called the magneto rotational instability. Okay? So this is probably an essential ingredient in explaining how stars are formed, how protoplanetary disks manage to come together, how black holes function. And the magnetic field is a critical part of this. Where does the magnetic field come from? This is a great question for dynamo theory. The current thinking is when you take these systems to very high values of magnetic Reynolds number, they exhibit what's called a subcritical transition. You don't need to seed it with a magnetic field. This turbulence itself can spontaneously self-generate, much in the same way that turbulence in a pipe flow self-consistently reinforces itself. So the critical Reynolds number for turbulence onset in a pipe is 1700 experimentally, but it's laminarly, it's stable to much higher values if you calculate it analytically. The same sort of thing appears to be true here. Very, very small amounts of magnetic field are able to maintain a dynamo in these systems. So accretion disks are ripe for study, and we can study these using Couette flow. Okay, and so Couette flow, there are a class of experiments studying the magneto-rotational instability as a step to dynamo studies. And an example of that is a liquid metal experiment done. This one is being done at Princeton. There are other liquid metal experiments, one in New Mexico and others around the world. And the idea here is you have two rotating cylinders, one on the middle and one on the outside, that spin at different speeds. That's what Couette flow is. And you can set up flows which mimic the Keplerian flows you have around central objects like black holes. So we can add value by using plasmas instead of liquid metals. And this is, so we're doing this at Wisconsin. And I'm going to use this to show you how we stir plasma. Okay? So just a reminder, Couette flow is flow between two rotating cylinders. And by controlling the rotation on the inside and the outside, we can set up differential rotation. So this is the flow speed and the computed velocity field versus radius in this cylindrically symmetric system. If you make the center spin at 3 kilometers per second, the outside spin here, you get a flow that looks something like this. I can also do something very simple, like just spin the outside. And if I just spin the outside, I would get a flow that looks like this. This is essentially a viscometer. The profiles which get set up can be used to measure things like viscosity. It's a classic fluid experiment, and it's maybe the simplest possible 2D-like experiment. Okay? So what's interesting about this is you can show that this case, the blue case, where I spin the outside and the center is moving slowly, this case is stable to all perturbations. It doesn't have any turbulence at all. If you make the center spin and the outside is stable, it turns out, and the outside is fixed, one gets instabilities called Taylor vortices that develop, and so instability sets in. Keplerian flow has this funny property that the velocity drops with radius, but the angular momentum increases with radius, and you can show that this is stable to these Taylor vortices. But it can be destabilized by this magneto-rotational instability. So we've set out to try and do this experiment using plasma. And so I'm going to tell you about a geometry, and the geometry is as follows. We're going to use rings of permanent magnets that create a very high order multipole field on the boundary of a vacuum vessel to hold an unmagnetized plasma. So each of these black dots is a ring of permanent magnets around a central column that are symmetric about that axis. So this is a ring which goes all the way around. This is one that goes all the way around. And the north pole points up here, and the south pole points up here. So the magnetic field lines go from one magnet ring to the next, like this. Okay? Because these things are in opposition, they nearly cancel each other. This magnetic field almost perfectly cancels this field. So up here, you don't see these magnets. In this region, there's no magnetic field at all. And this is just a property of the very high order multipole dropping off with radius from the edge. Okay? So there's this big unmagnetized area, and the magnetic field that's around here can be used to keep plasma off the wall and confine it so that it can become hot. And that allows the temperature to be big so the magnetic Reynolds number can be big. Okay? Now the other thing I can do here is I can introduce into the edge cathodes that inject current. So here's the north and the south poles. I can drive current from a positive to a negative anode, driving current across the field. The current is in, the magnetic field is down. There's a torque which causes the plasma to spin on the surface of the plasma in the magnetized edge. Okay? So currents are going to flow in the plane across the magnetic field. The magnetic field is in the plane. Those currents are going to flow, and it's going to cause a torque to act on the plasma so it spins. Okay? Okay. And so an electron coming off of here, what it will do is, so you are literally boiling off electrons from the cathode, and I'll show you more about that later. What will happen is it'll very quickly establish a plasma on a single field line because the transport of plasma along field lines is fast, and it will make that field line an equipotential. So that field line will now be a constant voltage, and it will then drive current across. There will be current that flows perpendicular to the field everywhere here. And that's, I think, the point. Okay. Now, here's a peculiarity about plasma and magnetic fields. The viscosity of plasma depends on the strength of the magnetic field. And I'll come back and I'll show you more about this later. But if I plot the magnetic field strength is I have magnetic field on the outside and magnetic field on the inside. And the magnetic field drops off. I have this magnetic field free region. The plasma is extremely viscous in the central region and not so viscous at the edges. And this is a property of the way magnetic fields control plasma viscosity. Okay. It's theoretical. I'm going to come back to this point. I'm going to come back to this. It's easier for me to make the point going at it here. Okay. So we've done the same thing. We've done the same thing in a spherical geometry. And this is a much bigger experiment which is intended to demonstrate dynamos. And this is a 3-meter diameter spherical vacuum vessel. And I'm going to illustrate the geometry. We're going to look inside it in a second. You can see there are lots of ports that you can look inside the plasma from various positions. Probes can be inserted into the plasma to measure various things. And if you look through this pole right here, this is what you would see on the far side. You would see these rings of permanent magnets that are bolted to the inside of the vacuum vessel. Okay? And this is what you see when there's plasma present, and this is what you see when there's not plasma present. These bright spots are hot cathodes that inject fast electrons into the plasma. We apply a potential to them. The electrons are driven off of the cathode. Current is injected. And these fast electrons, which are emitted, do two things. We use them for stirring, like I mentioned. They're also used for heating and heating the plasma. They're the source of energy that makes the plasma in the first place. Okay? So this plasma has magnetic fields that are created by these rings. If you plot what the magnetic field strength is in a spherical geometry, similar to what I showed you before, these rings look like this. I have a very high order, an L equal 36 multipole for the magnetic field. The center is completely unmagnetized. Okay? So again, I told you earlier that we wanted to have high Alfvén Mach number flows. This is harder to do in a plasma because even something like the Earth's field or a weak field can make the plasma magnetized. So plasmas, because they're so diffuse, it gets harder to satisfy that. Okay? So this confines the plasma. This is what it looks like. These are the magnets that are bolted to the wall. So these are super strong samarium cobalt magnets that are bolted to the wall. These point inward, these point outward. And these magnets are large, so they have an enormous amount of stored energy. They're very strong. If they get too close to each other, they are attracted to each other, and so assembling this gets very tricky. So for example, just to illustrate that, you can see what happens when these magnets get too close to each other. They hit with 250 pounds of pull force, and they collide and they destroy themselves. They're very, very powerful magnets. So we have 3,000 of these on the surface of the sphere holding the plasma in place. The cathodes, these are two of the cathodes. What the cathodes are it's a special type of ceramic called lanthanum hexaboride that emits electrons. It has a low work function, and it has a it can emit and it has the ability to source a large current. And so we put these into the plasma and we bias them with a voltage of something like 400 volts relative to an anode. So we draw current from a cathode to an anode, and the currents are typically on the order of 100 amps. And so this gives something like 36 kilowatts of power to go in and heat the plasma from each of our cathodes, and we have many of them. Okay? So this is just a little bit more detail about that. So the magnetic geometry here, this gets back to the thing that Andy was asking about. So plasma has this special property that when the particles are magnetized, they carry out circular orbits around the magnetic field lines. When the plasmas have the temperature that they do in our machine, the electrons have very, very tiny orbits around the magnetic field lines. They're less than a millimeter in size, but they're free to move along the field line. And what this gives is it gives particle orbits that bounce back and forth between the high field region at one side and the high field region at the other side. And the plasma can only be lost over a tiny, narrow region to the surfaces of these magnets. And so we've actually you can do things like measure. Here's a close-up of one of our magnet rings. You can see the plasma burn mark on the magnet. It's very narrow. It's about 1 millimeter in size. So plasma is only being lost to this tiny ring. We've greatly reduced the loss area to the wall by introducing these magnets. And we actually built a probe with a set of electrodes on it that could measure the width of the loss across this. And you can see the width is about 1 millimeter in size. So this is a measurement of the probe of the plasma loss rate to the wall, and it gives this tiny loss area. Okay, this may be too much for this lecture. One interesting thing that we're finding is it greatly exceeds what the theoretical prediction was supposed to be, and so we're trying to understand that at this point. But from the standpoint of dynamos, okay. So the way this works is we start with the vacuum. We inject some gas into the plasma, into the vacuum vessel, a small amount. We change it from nearly perfect vacuum to just good vacuum. So the pressure is 10 to the minus 5 atmospheres or so. It's hardly anything, hardly any particles at all. This corresponds to densities which are something like 10 to the 18 particles per cubic meter. So it's a very diffuse gas. Then we turn on these cathodes. The cathodes have a high voltage. They put power into the plasma. And this is showing a plasma that is operating for about 3 seconds, 2 seconds or so. And it has about 200 kilowatts of power. So the power, because the plasma is confined on the surface, we have a lot of power going in. That goes into heating the plasma. This shows a measurement of the electron temperature. It's about 15 eV or so, okay? And the density in this case is, okay, so this is where I was going with the Couette experiment. So the plasma ends up to not be perfectly ionized. The neutral gas is in there, and there's plasma. We separate those two out. We think about the plasma density being the density of the electrons and the ions, which have to be roughly the same. And we have some neutral gas particles, which will represent a source of collisions for the particles that can add to the momentum, add to the fluid equations in some way. And we've been working very hard to make the plasma as fully ionized as possible. Okay? So this is a case where about 50% of the particles we put in, the ionization fraction, it become ionized. Okay? Yeah. So we use usually noble gases. So we use things like helium or argon, and we could use hydrogen. We could go lighter. One interesting thing is that the viscosity depends very much on the density, the mass of the particle that you use. So by changing the gas, we can also change the plasma viscosity. Right, so all we need is one ion, one electron to be stripped free. To strip the second electron from helium costs a lot of energy, that's true. But to make it singly ionized is straightforward. Actually, this makes the point. So we can do this with different gases. This is an argon plasma. This is a helium plasma. Argon tends to radiate a lot of its power, so this is a measurement of the radiated power. Because there are so many electrons in atomic orbitals, the plasma bombards it, and most of the energy comes out in the form of radiation. So we get higher electron temperatures by using helium because it doesn't radiate as much. Much of the energy, almost all of the energy, comes out in the form of radiation from argon. So, okay. So let me show you an example of how we stir the plasma using this concept of cathode stirring. So again, we have this unmagnetized region. We have the magnetic field here. We have cathodes that we can put at any latitude that we want. We can insert them into the edge or through the edge. If we put them in far enough, they're in the unmagnetized region in the center. We also have anodes that are adjacent to the cathode, so that we can drive currents to the anodes in some way. So if I pull some cathodes back into the magnetized edge, that gives me this geometry that I measured. Where I pull the cathode back in, I have the cross field currents that gives me the torque. Okay? So by varying which cathodes I pull into the edge and where I place them, in essence, I have a knob for controlling the rotation as a function of latitude, which is what I showed you at the beginning for my boundary-driven flows. I told you that if I could control the rotation on the boundary of the plasma, I would have a way of doing that. So this is the essence of the experiment. And so now I'm going to show you the results. Where I pull these two cathodes back, and I have a probe that inserts into the plasma along this cord that can be used to measure the flow velocity on that cord. So we measure the flows using objects called Mach probes. So if you stick a piece of metal into the plasma, you can measure the current to it very easily. You can just you can connect it to a resistor on the outside and measure the voltage across the resistor, and this tells you how much current is flowing to the probe. Then by applying a potential to that surface, you can control whether or not you're collecting the ions or the electrons and learn something. So if you bias it very positively, you collect all the electrons. The electrons are attracted to a positively biased electrode. If it's negatively biased, ions are attracted to it. You can learn lots of things about the plasma by sweeping the voltage and measuring things. If we bias each of these tips into a mode where all they do is collect ions, so we bias it quite negatively with respect to the potential, I can measure the difference in flow to two different sides of a probe. I have two metal probes separated by an insulator, and the difference in the flow to the two sides can be used to measure the velocity of the plasma. Okay? And by positioning the probe then wherever I want in the plasma, I can measure what the velocity is. This could be generalized to 4 faces so that I could measure flow in 2 dimensions, for example, or even 6 faces where I measured the 3-dimensional flow. So we'll measure the flow along this cord, and here's an example of that flow. Yeah. From the cathode. So is that what you're asking? Right. So there are two things I'm doing here. One is these hot cathodes that inject current. I'm pulling those into the magnetized edge. They're putting lots and lots of current and power into the plasma. And the current that's emitted from this cathode, in order to go to the anode, which is over here, so I have a power supply that is trying to drive current between here and here. I have a large voltage between this point and this point. Current's going to try to flow from here to here. In order to get there, it has to cross the magnetic field. So current is flowing radially inward and then down, or if you will, it's flowing across the field here. And so that gives a force which is out of the plane, and this system is axisymmetric. It gives a force which is out of the plane and therefore gives a torque on the plasma to make it spin. It's local to this latitude. So at this latitude, in the northern hemisphere, I will make the plasma spin azimuthally like this.
For the same azimuthal angle, all the probes are raised to the right-based edge.
Good question. It's a little more subtle than that. It turns out, okay, so there's some plasma physics effects which enter in here. So one thing that you know, maybe you know about the magnetosphere. The magnetosphere has plasma in it. The particles bounce from one pole to the other, back and forth. And at the same time, because of gradients in the magnetic field strength, they drift azimuthally. So they perform what's called a precessional drift. And that drift ends up meaning we have the same thing here. The particles bounce back and forth along these points here. They're reflected at this point by the very strong magnetic field. But they also drift in the azimuthal direction so that they symmetrize the plasma very quickly in that direction. We inject current in, it fills up this field line, but then the particles drift in the east-west direction and very quickly symmetrize the flow in that direction. Okay? The same thing happens with any electric field that develops. So an electric field develops a drift. One way of thinking about the flows that we observe is that in the magnetized edge, the flows are equivalent to an electric field, a Lorentz force shifted electric field that causes the plasma to move. Or the flow velocity is essentially the reference frame in which the electric field goes to zero. So we make plasma using these cathodes down here, and we are going to stir using these two cathodes up here by pulling these probes back into the edge. And we apply a big potential to these to drive currents across the field lines. And this is the type of flow we get. This is the measured flow versus radius from the center. So we measure the flow along this radial cord, and we measure it here. And we observe that at the edge where the cathode is, I have a very high speed flow, and it viscously penetrates into the core where it's unmagnetized, and we're driving this flow on the inside. Okay? Right? At the same time, because we're driving flow in the azimuthal direction, there's a centrifugal force which acts on the flow to cause the poloidal circulation to happen. Okay? So earlier I showed you the simulations where I was stirring in the two hemispheres, stirring in opposite directions. Here I'm just stirring in one hemisphere, but I still get a poloidal circulation that starts to develop. Okay? And this is the solution to the Navier-Stokes equation that you get if you just stir in this region, and this is the poloidal circulation that you develop. We actually measure that flow here, so we can actually measure in the plasma both the rotation and the diffusion inward, as well as the poloidal circulation. Okay? So we're stirring plasma using this. Now, you can actually use this as a viscometer. We can solve the Navier-Stokes equation given what the fluid Reynolds number is. That's essentially a measurement of the viscosity. If we knew what the fluid Reynolds number is, we would know what the viscosity is because I know what the peak velocity is. That's what I'm measuring. So the details of how this fits and how the flow penetrates in depends upon how big the viscosity is. And we find in this case that the flow velocity is roughly consistent with a Reynolds number of 200, which is also consistent with an ion viscosity that has an ion temperature of about half an eV. Okay. Yeah. Right, we have, this is, you can see what the forcing is in the numerics here. We're only forcing it in this region. No slip. Yeah. Well, another way of viewing it is that the flows which are set up in the magnetic buffer region are in part determined by the transport through that region. It turns out there are flows that are small that are observed there, but they're set up by the self-consistent electric field that's present, and that's kind of a boundary condition of some sort that must match to the unmagnetized core as well. So there is a low velocity that has to match that, that it to some extent is much smaller than the velocities that we're imposing. So in this is V phi that we're measuring in this plot. Yes. It's going out. It's going around this way. Yeah, it goes to the outside. It flows to the outside. Okay, so this is what I was saying. So we can estimate what the viscosity is from the theoretical formulas. And the viscosity is different in the magnetized edge from the core. So in a plasma that's unmagnetized, like in a gas, the viscosity is set by the mean free path between the collisions and the characteristic velocity of the particles which are bouncing around. So this is just the gas theory, the kinetic theory of viscosity in a gas. That's what's governing the central region. So this is essentially the the collision time between ions times the thermal speed of the ions squared. This gives a scaling. The collision time becomes shorter when the density is high. And the thermal speed increases as temperature squared. The collision time also has a temperature to the 1/2 factor in it. So this gives an overall scaling, which is the temperature to the 5 power and a density in the denominator. So the viscosity has this very strong dependence upon the ion density and the ion mass and the ion temperature. So one way of viewing this is that we have a measurement of the, that we're measuring the ion viscosity. One way of viewing this is that we're measuring the ion viscosity. Another way to measure, and we would actually be able to check whether or not that was the right viscosity if we measured the ion temperature. And we're only just beginning to be able to measure the ion temperature and compare against that. What we see is that the temperatures are roughly consistent with this, and so the viscosity we measure that's consistent with this Reynolds number seems to be working. When you move into the magnetized edge region, the viscosity is again set by a characteristic step size, but instead of being a thermal velocity times a collision time, it's now set by the Larmor radius of the gyro orbit of the part of the ions about the field lines. Because in the edge the plasma is strongly magnetized, the viscosity becomes quite small. So the profile of the viscosity in the plasma is enormous viscosity in the center. It drops down to something like 0 as you move closer and closer to the outside. Okay? And so what we do when we model this is we only model it inside a radius which is in the unmagnetized region. So we don't try to model the entire sphere where the cusp field is. We just model the region which is interior to this. Okay? Electron temperature is something like 15 eV. 15. Right. So there are two things happening here. I'm making plasma and I'm heating it. The heating almost all goes into the electrons. So I'm injecting these fast electrons that are colliding with the background electrons and heating them. The electron's energy is dissipated in two ways. One is it's lost to the walls, and the second way is it can collisionally exchange with the ions. The ions are also being lost to the walls. But because the plasma is being lost at some fairly rapid rate, it turns out that the ions never get a chance to catch up. They never thermally equilibrate before they're lost to the wall. So it has to do with the finite confinement of the experiment. Right. So the electron temperature we measure by sweeping the voltage on a probe and measure how the electron current changes with the applied voltage. So the electrons have a Maxwellian distribution. They have an energy distribution which is characterized by a Boltzmann-like distribution. The very fast particles are able to get over a large potential and escape to a probe. The low energy ones don't. By sweeping the voltage, we can measure out the distribution function of the electrons and infer its temperature. The ions, the way we're actually measuring the ion temperature is to look at the Doppler shifted emission light from an ion line. So atoms emit light because they're being continuously bombarded by electrons. There's excitation of optical radiation. If we have an ion so helium has 2 electrons normally. You strip one away, you still have 1 electron left. That singly ionized ion also has atomic radiation that can be measured. And by measuring the Doppler shift of that, we can infer the temperature of the ions. So that's how we're measuring it. Okay. So I'm afraid I'm missing some of the slides that I was initially intending to show. But I can fix that. So we're now doing experiments where we have control over the rotation in this hemisphere, and it's different from this hemisphere. So we can make this hemisphere spin one direction, and we can spin this hemisphere in a different direction. And the poloidal circulation that we expect to develop is here. So again, this is a solution to the Navier-Stokes equation inside this domain, which is away from the walls. And we have these 4 cathodes which are now stirring, and we're able to measure differential rotation in the two different hemispheres and estimate the fluid Reynolds number and the magnetic Reynolds number for this case. Okay? And this corresponds to parameters like I was showing you at the beginning. Fluid Reynolds numbers, which are, in this case, a little bit higher even than the magnetic Reynolds number, which is about 400 in this case. Okay? So, I think what I need to do, you've got to bear with me for a second. I think we should take a 3-minute break. Everybody stand up and stretch, okay? I'm missing some of the slides that I thought were in here. That I think in my stupor, I saved the wrong presentation in the wrong place, so I really apologize about that. Let me just say, you asked a question about who was asked the ion temperature? Somebody asked about the ion temperature. This guy here. Oh, okay. Well, one way we can measure the ion temperature is by measuring the very high resolution Doppler shifted emission from the plasma. So this is the image of Fabry-Perot rings for line emission coming from the plasma. If you sum over this, you can, from the width of the interference pattern, you can infer what the Doppler shifted emission of the plasma is, and back out something like what the ion temperature is. So this is what the emissivity is, and this tells us what the temperature is, and we can do scaling experiments. So for example, we vary the input power. As the power goes up, the ion temperature, which is measured here in green, goes up in argon. So for argon at high density, the ion temperature can be as high as several eV. So we measure the ion temperature in real time. So now, where are we going with this? The idea is next what we'll be doing is we'll be completing, we're now carrying out experiments where we have 12 cathodes at each of the latitudinal positions, and we're going to be measuring the flow at 16 different chords that all go in, so we can measure the two-dimensional structure of the velocity field, and we're going to be optimizing the boundary flow to create the conditions for a dynamo. So the dynamo depends very much on the details of the velocity field that we impose, and so we're in the process of carrying that out. Let me show you the sort of thing that will happen. This is a simulation of a very boring dynamo where we stir this hemisphere with the plasma parameters like the ones I've shown you, a relatively high viscosity plasma, Re of 200, magnetic Reynolds number of 400. And what happens in this case is the magnetic field simply grows up and saturates. And the saturation value depends upon the strength. It depends upon how fast it flows and the mass of the ion. So the characteristic equipartition value, if you will, is, as we talked about earlier, let's see, I need an eraser. Is there? Yeah. This is an eraser. So we measure, so in equipartition, b squared over mu naught is equal to rho v squared. That's sort of the estimate of how strong the magnetic field can get. So if we drive the flow with some particular speed, we can estimate how big the magnetic field will be. It will be on the order of some mu naught times the density times the characteristic flow speed. So that's what the saturation value should be. We normalize things in these units. Going to higher density and higher mass for the ions can greatly influence this. So if you use a light ion like helium at this density, these things saturate at about 1 Gauss, which is not all that high. So it's a very weak but very measurable field. By using something like argon, it ends up being 30 Gauss, which is much bigger than the strength of the Earth's magnetic field, for example. So this is the type of thing that we're expecting for these laminar dynamos. And so this just illustrates more of this. So this is the type of flow we're trying to drive. It actually requires counterflow in these regions, positive flow in these regions, and if we use this, you get the transverse dipole. The strength of the equipartition field that you get is bigger in argon than it is in helium. There's this mass scaling. Okay. Now let me show you something else. And this is kind of a Gedanken experiment, if you will, for what might happen if we played with the numbers in such a way that, that we might control the onset of turbulence, and we might be able to go to a very high magnetic Prandtl number. So we talked about fast dynamos and slow dynamos at the beginning, and I made the point that in order to make a fast dynamo, we need a fluctuation-driven. We want chaotic flows, and you can do that with turbulence. And it's most efficiently done if you have a high magnetic Prandtl number. So this is going to be a simulation where I show how we stir at the edge. I'm going to start out with a nice laminar flow. It looks something like this. I'm going to increase the fluid Reynolds number until it becomes turbulent. The onset for the first fluid instability is about 300 or so. Above that, you'll start to see fluctuations in the velocity field that are representative of turbulence beginning to play a role. In any case, we get chaotic flows, and if the conductivity can be made sufficiently high, which we can do by heating the plasma to an extremely high temperature, this system exhibits the following behavior. So here's what happens. You start out with this laminar flow. We increase the fluid Reynolds number, and you start to see some wobbling as it adjusts, and it kind of settles in. And then we increase the fluid Reynolds number even further, and now you start to see turbulence setting into this flow. And then at this point, what we're going to do is we're going to inject a little bit of extra power into the electrons, maybe through microwave heating. And the conductivity is going to become large. And in this plasma, we start to see small-scale magnetic fields. This is what we would see if we were able to create these plasma conditions. We start to see a small-scale fluctuation dynamo present. Okay? So in this case, it has very different characteristics than the large-scale laminar dynamo that I showed you. But this is another direction that plasmas can take us, and we can go in that direction because the magnetic Reynolds numbers can be enormous. Okay? So I thought I would show you several other.
So this is a simulation. You're going through the experiment.
Yes, we're now stirring plasma. We're controlling the flow on the boundary, and we're set up to do laminar large-scale dynamos. The fluctuation dynamo happens only with a higher electron temperature than we have presently, and a fluid Reynolds number which is consistent with what we have.
Does it saturate the simulation?
It does. It saturates at a relatively low level, but it ends up to be on the order of 0.4 Gauss or so, we would see fluctuations that would be easily identifiable. Okay, so here are the slides that I was missing earlier. Sorry about that again. So let's go back to the Couette flow. So in the Couette flow, we learned a very important lesson about how plasmas are usually more complex than you might have initially thought. And one of the effects we discovered was that the neutrals played a very important role. So I'd like to show you how the ionization fraction, remember I said that when we ionize the plasma, only some fraction of the electrons are stripped from their ions. The gas is a mixture of ions and neutrals that are present. And what this gives is it gives a momentum equation which is a little bit more complex than the one that we started with. We still have the viscous term, which is causing the ion momentum to diffuse inward. But in addition, there's a term which is a momentum loss rate that comes about due to a process called charge exchange. So charge exchange is a process by which an ion is moving along, it bumps into a neutral, the electron jumps from the neutral to the ion. The neutral particle, which is now moving very fast, can escape to the wall. The momentum is lost. The ion, which is left over, isn't moving. And this represents a big drag on the momentum. So in a partially ionized plasma, in this case, the momentum is governed by is governed by an additional term, which is a drag on the flow. Okay, and there's a characteristic length that goes into this, which is the charge exchange time and the viscosity, and you can characterize a characteristic diffusion length for that, and you can show that this equation in cylindrical geometry has Bessel function-like solutions. Okay, so this if you ignore the magnetic field part in the unmagnetized core of the plasma, this set of equations has Bessel function-like solutions. So in the Couette experiment, what we found was we were able to stir from the outside, letting the inside do whatever it wants. The momentum diffuses inward, but it deviated from the straight line profile that we expected without any drag. The curvature of this line is representative of the drag term, which is acting like a body force to cause the momentum to drop more rapidly. Okay? And so one of the things that we've learned from this experiment is that partially ionized plasmas are not particularly good because they represent a drag term that causes the velocity to be something other than the simple Navier-Stokes equation that we were using to solve for the flows. Okay, so we've worked very hard. I'll come back to that in a second.
There's no magnetic field.
No, there's no magnetic field in this setup. Right. So there is, but there isn't. The magnetic field is localized near the edge by permanent magnets that are confining the plasma. In the center, the field cancels and is basically it's field free in that region. So that's the region we're studying. So one of the things that this curvature allowed us to do was very precisely fit. Since we know what the neutral pressure is, we were able to very precisely measure the viscosity and compare it to the formulas that we had predicted from theory.
So the argon V5 was pretty straight.
Yes.
And HEV5 was quite flat.
Right. So that's a good point.
The new term is increased with the
So argon is a very, very heavy ion, which means it's lost slowly to the walls because it's heavy. It doesn't flow, its sound speed is slow, so it takes a long time to get there. We can ionize it with a much higher ionization fraction. The higher ionization fraction means that there's less curvature because there's less charge exchange drag taking place. And that's exactly what you're seeing. So the higher ionization fraction is an important point here. Okay? The helium, in this case, was only 0.6% ionized. And correspondingly, the neutral density was higher by a factor of 100. And so the charge exchange drag on the ions was quite high. Okay? So the point is the ionization fraction is very important.
In the actual momentum equation, that term is presumably isotropic, and you just written down phi.
Only the phi component and without this.
Yeah, but if you restore the full equation now, you would expect that V5 to be replaced by a vector V.
This one here.
Yeah.
Yes, absolutely. Right, so if we were solving in the sphere, for example, with colloidal flows, we would expect that charge exchange to be important. Right. Okay. So in this Couette experiment, we actually we had installed a center post with these permanent magnet rings, and we stirred from the center boundary as well. So I told you that if you stir from the outside, it's perfectly stable to the magneto-rotational instability. If you stir from the inside, you might be able to set up a configuration where the center spins at one speed and it drops as you move to the outside, and set up the conditions in which the magneto-rotational instability would be observed. So this is the sort of thing we get in that case. Here what we do is we ionize the plasma, or we puff some gas in, and then we let the neutral pressure drop with time to maximize the ionization fraction and get as little neutral drag as possible. So I'm going to show you a movie here. What happens as you go through this, you can see that as the neutral density drops, the flow velocity comes up. We're stirring both on the inside and on the outside, and this system, the flow speed comes up to its highest speeds when the ionization fraction, the density is basically constant. The neutral pressure is dropping by a factor of 5 throughout this shot, and so that neutral pressure is playing a big role. So the hydrodynamics seems to be controlled in part by drag on neutrals in plasma, and this has been something we've been fighting to some extent. Okay, so on the big experiment, we're benefiting from a very large volume and a much smaller loss area. We used much stronger magnets, so the loss area was greatly reduced. The bigger volume means that there's more volume for creating plasma. And you can think about this in the following way. The plasma production is governed by the electrons colliding with the neutrals. It's volumetric, so the number of electrons being created per unit time is a ionization rate times this factor here. So there's a volume that goes into this. The rate at which plasma is lost is something like the loss area to the probes on the surface times a speed, which is a sound speed that the plasma flows into the wall. Okay? If we make the volume bigger and the loss area smaller, we can create a plasma at a much lower neutral fraction. Okay? So the loss area to volume ratio is a really important player as far as determining the ionization fraction. In this case, this is argon emission from a series of chords that go from the center outward. We are looking at two emission lines. One is from neutral argon, which is, and one is from a singly ionized argon. And what we find is that there isn't any emission coming from the neutrals from the core. We see ion emission all the way to the core, and these neutrals are effectively burned out. They can't get into the core, they can't penetrate. The characteristic distance over which they become ionized is several tens of centimeters, and this plasma is fully ionized. And so one of the neat things about going to a much bigger experiment is that the ionization fraction has become basically 1 in these bigger plasmas. And that's the effect that I wanted to show. Okay? So I think I'm going to stop there, and I'm going to take questions. I've tried to show you in the first part of the talk that we have some theory which illustrates how we might build dynamos. I've talked about buildable dynamos and how we can control the flow from the boundary, and we're now doing these experiments in plasma where we have control of the rotation on the surface of the plasma. We're in the process of doing plasma hydrodynamics where we're measuring plasma viscosity, the ion neutral drag. These things end up playing a role. We're able to get to plasma parameters which should quite easily turn into a dynamo if we can stir it properly. And so measuring the flow and stirring the plasma is where we're heading at this point. So with that, I think I'll stop. Yeah.
So this experiments, is there a lot of heating around, like you are using a lot of power to stir?
Right, so there's something like 350 kilowatts of power going into the experiment. The surface of the sphere has cooling channels of water built into it, so it's continuously being cooled so our magnets don't get too hot, for example. Yeah.
And is like you had probes to measure velocity, is it possible to have throughout the 4-pi surface?
To do what?
Like probes to measure velocities.
Yes?
Is it possible to have all 4-pi direction, like throughout the sphere?
To cover
the entire.
No, we can stick probes in at different latitudes, but at one toroidal location. We can't cover the whole sphere. It would be nice to measure the the three-dimensional properties of the turbulence, for example. We can't. That's hard for us to do. In 2 dimensions, maybe. Is it what?
The second purpose is to confine the plasma.
The magnetic fields have 2 parts. One is to confine the plasma, and the second is to provide the magnetic field for the torque.
So how does it confine the plasma?
So it has to do with this idea that if you have a magnetic field line, there's a Lorentz force perpendicular to the field line which causes the particles to gyrate around the field in this way. The diameter of this is tiny. For the electrons in our experiment, it's less than 1 millimeter. The ions is maybe a half a centimeter or something like that. If a particle comes from the outside, comes from the center, as it moves downward and encounters the magnetic field for the first time, it feels the Lorentz force that simply makes it turn back and go into the plasma like this. So you can think about this as basically being a reflecting wall that causes the plasma to bounce off of this spot. So our cusps, our permanent magnet rings, are really good at making the plasma, keeping the plasma from going out in this region. But there's one line, there's one magnetic field line right down the middle between these two where the plasma can escape. So there's a small region where it can escape. The particles here, if they come in at the right angle, they can work their way down and escape. But otherwise, most particles are simply reflected specularly out. That's a great question. So the status of that, the status of that experiment is as follows. So we're not able to make the center spin as fast as we would like yet. And we'd like the velocity to be decreasing with radius. So the unmagnetized region goes from 0.1 to 0.3 in this Couette experiment. What we'd like is we'd like to just, in principle, not stirring the outside and stirring the inside would give us Taylor vortices. And the problem has been that we haven't been able to make that plasma yet. In any case, this is what we have been able to do. You can see the curvature that comes from the neutral drag. And so we're upgrading this experiment to have stronger magnets, make the volume bigger, and get rid of the neutral drag. And
So at the moment, you're not putting in enough power at sort of R equals 1.1.
exactly.
That's where you need to-
Exactly.
I'm trying to do that.
We're trying to do that. So the experiment, we're increasing the strength of the magnets, making the volume slightly bigger, and that should allow us to get rid of the neutrals, which we've observed in the big experiment. And
Presumably, there's provided the force sufficiently on the inner cylinder, the neutral drag won't stop taking vortices.
no, I don't think so.
So it's a sort of baby drag, isn't it? So
Right.
it won't protect.
It'll make it drop off more quickly.
Yeah.
It may be too viscous. Right, exactly. So I showed liquid metal dynamos that worked, and I showed the spherical one, which was not a dynamo, where we measured the turbulent EMF. And that was done by applying an external field from coils outside to probe how the turbulence modified the field.